Hi, Ku.
Hey, hello, Justin.
Hello. How are you doing?
Okay, I'm good. You can see I'm still in my office.
Yeah, I'm in my
Uh,
room. Yeah, just a white
okay.
background. Yeah, different
Yep.
different background for you today.
Yeah, different background for me today. Since can sort of go back to office for a while, right? So that's why I'm back. I'm back in the office. So you see, I got my like whiteboard and all this, so I can do my writing and thinking and all this. Yeah. So that's why I'm in my office. Actually, I like my office a lot more.
Oh, nice.
Okay.
Okay.
So anyway, yeah, so for the audiences, welcome to the DataScience SG meetup again. Still virtual meetup lah. So we're still waiting
Yeah.
for phase 3 to come. Then we'll think about whether we can do a physical meetup. But for now, audiences, please hold on to your chairs. Hold on to your chairs and computers. We will still do our virtual meetup. So, Justin, how are things?
Good. Yeah, still looking forward to going back to the office. Yeah, I've
Okay.
been working from home for more than 3 months now. Yeah.
Mm, okay.
So yeah, I
Hey,
think.
oh, for the data science SG community, right? Y'all must have seen Joey quite a long time, right? Then after that, a lot of time, then y'all haven't seen Jiaxing, right? So I'll let Jiaxing introduce herself. Ah,
Yeah, I joined I think a little more than 3 months ago. So yeah, I've been appearing a bit more and getting used to live streaming events. Yeah, so yeah, I think before we begin the session, let me just briefly introduce who we are and what we do. Yeah,
yeah.
Google Developer Space is a platform for developers and startups from around the region to learn, connect, engage, and be inspired. As part of the developer relations team, we aim to empower and connect the community to our people, programs, network, and technologies, be it in person like a couple of months ago or online like today. Without further ado, I'll hand the stage over to Ku from Data Science Singapore to share more about today's session. Over to you, Ku.
Okay. Okay, thank you, Jiaxing. Okay, so good evening, everyone. Welcome to the Data Science SG meetup for September. So today we have 3 speakers, but 2 talks. And I think for the first talk, right, will be on sample counts in elections. So I think a lot of us in Singapore, we had our election 2 months ago, and it was sort of some of the results are a bit nail biting, even though we have seen the sample counts and all this. Without much further ado, let me bring the speakers to the front first. Then I'll let them introduce themselves. So I'll go to bring Shen Ting and Yong Sheng now. Hello, Shen Ting. Hello, Yong
Hi.
Sheng. Hi. Yong Sheng, your mic, you're mute. Okay. So, yeah, Shen Ting, you want to introduce yourself, then maybe followed by Yong Sheng.
So I think you guys have heard me speak a few times at DataScience SG. I'm currently a data scientist at INSEAD.
Yong Sheng.
Hi, I'm Yong Sheng. I'm a research scientist at Institute of High Performance Computing at A-Star. So I got my PhD in applied and computation mathematics. So my research interests are in mathematical optimization.
Okay. Yep. Thank you, Yong Sheng. Thank you, Shen Ting. So I think without much further ado, let me get them up to speed. Then I'll go to bring. I think Shen Ting can start sharing. So Shen Ting will go first. Then yeah, let's go back. Let's go to the backstage testing and yeah.
Okay, so the title of our talk is Sample Count in GE 2020. So it's a joint talk between myself and Yong Sheng. Okay, so earlier this year, right, we had actually almost 2 months, exactly 2 months to the date. It was polling day. And my personal experience was that in the morning, I saw very long queues downstairs because I live quite close to a polling station. But by early afternoon, when I voted, it was a lot better. And at 5 p.m., the elections department actually announced that the polling hours will be extended by 2 hours to 10 p.m. So for most of us, that's fine. It just means that results are delayed by 2 hours. But for poor election officials, this meant that they had to work an extra 2 hours on a really very long day. Okay, so but for most people, the common complaint that I saw on Facebook was, but I want to go to sleep. I want to know the results. And the sample count was now delayed to be maybe about midnight expected, or maybe shortly after midnight. So I guess the question now is, with the sample count, for those people who want to go to sleep early, is it accurate enough that, you feel like you can go to bed? But first of all, what is the sample count? Okay, it's relatively new. It's was introduced first in GE 2015. So the idea is that at each polling station, they will randomly sample 100 ballot papers, and when they're at the counting station, and they will add these up for each of the polling stations to give you what is the sample count. Okay, and they only take valid votes. So if they pick up the first 100 votes, there's an invalid vote in there, they'll pick another one just to make up for it. Okay, what is the rationale behind the sample count? So from the ELD website, they do say that the sample count helps prevent speculation and misinformation, and it also allows for officials to check against the final election result. So it's meant to be indicative that when you actually get the results, you don't think that you don't get a huge shock. Okay, but back to our original question, right? Can I go to bed? So the idea is, further sample count is from 50-50. Obviously, the more certain that you are with the outcome, that's the intuitive idea. But obviously the question is by how much, and that's what I want to calculate. And is this the same margin for every SMC and GRC? The short answer to that is no. And we'll see why. Okay, so I actually got this idea, on the day itself at maybe 9 or 10 p.m. So what my idea was that I would do Google Sheets. I would update the sample count in real time, and I'll calculate what is the probability of win. So once all the sample counts are in, you can see which SMC or GRCs are still in play, and then you can decide if it's worth staying up to wait for the actual results. Okay, so I talked about probability of winning. So given the sample count, what is the probability that the actual result is not in favor of PAP or opposition party? You can set it up either way, right? Most of the contests are it's just a straight up fight. Or given the sample proportion, what is the probability that the population proportion is less than 0.5? It's actually the same problem. And this is just a more statistical way of defining the problem. Okay, so we use this idea from statistics called the central limit theorem, which states that if you have n independent random samples, and say you have a sample mean and the variance is, a typo, is sigma square, then for large n, the distribution of the sample mean is approximately normally distributed. It's going to be mean p, and the variance is going to be sigma squared over n. So how do we set this up? Okay, the sample count proportion is going to be what we define as p hat. It's just what you get from the sample count proportion that is reported. And for your binomial, your standard deviation is just going to be p times 1 minus p, and then divide by n. Because we have using the central limit theorem, we have that the variance is going to be p times 1 minus p. So the distribution of your actual proportion is normally distributed just with a mean of p hat, and your variance is going to be p hat times 1 minus p hat divided by n. And one thing about the central limit theorem is that you need a fairly large n for the approximation to work well. And in the worst case, this is actually going to be Potong Pasir, which only has 6 polling districts, i.e. 6 polling stations. So this is actually large enough for the approximation to work. And you note that the variance is actually dependent on the number of samples. So this is why we said that is the margin going to be the same? It's not, because it's dependent on how many votes are actually sampled from each of the districts. Okay, so you're going to see this slide again later. The caveat is, of course, ELD said that they do some weighting of the votes based on the size of each polling district. So we don't actually have the raw kind of like samples from each that is reported. But if you assume that the number of votes at each station is comparable, then the approximation should hold. And we're actually here doing a sampling without the replacement. But in the central limit theorem, we're actually doing a sampling with replacement. But again, if the sample count size is a lot less than the number of voters, then this is not really an issue. The approximation still holds. And in practice, the sample count size is only about 3 to 4% of the actual number of voters in the entire SMC or GRC, or even less. So this is a screenshot of what the spreadsheet looked like. It's not a complete spreadsheet. There's a link in the slides, and you guys can look at it later to see what is the actual spreadsheet like. One thing that is maybe slightly disappointing is that the ELD only gives integral values for sample count, meaning that, like say for Aljunied, they gave it to be 40, 60. And we know that it's a weighted average, and it's more than 100, right? So you expect to actually see decimal places, but no, ELD just gives you rounded to the nearest whole number. So one possible improvement that I could do to this is to actually account for this and do a plus minus 0.5 calculation to find what's the minimum or the maximum win probability that based on the integral values given by ELD. So based on this, I was actually quite confident that, say, Sengkang would be the second Workers' Party GRC, and I was also very confident that East Coast was still going to be won by the PAP. So conclusion, I could say that there's nothing really worth staying up for after this year's sample count release, because there were only 2 places where there was a small chance of an upset, which was Marymount and West Coast. And as expected, the actual results was actually the same as all the sample count results. So yeah, no, is this the end of the talk? Actually, no, it isn't the end of the talk. Actually, there's more to this, right? And I will let Yong Sheng continue.
Next slide. Okay. Next slide. Okay, thanks. Okay, so we'll switch gears a little bit here. So what we're going to do is actually ask a slightly different question. What we're going to ask is the question whether the sample count did a good job of estimating or predicting what the actual vote share for each party was like. Okay. Now, so let's start by just looking at the numbers over here of what happened on polling day. So in this slide, what I have here is the results for G 2015. Just for the SMCs only. First column are just the names of all the SMCs. The second column is the percentage of the votes that went to PAP. This excludes all the. This is only the fraction of all the votes that were valid. So I'm just going to exclude those that were spot. Third column is the sample count that was recorded on polling day. And on the fourth column is just the difference between these 2 numbers. So just a difference between the 2 percentage points. It's a very crude measure to just sort of figure out how different the sample count was from the actual percentage of the vote share that PAP got. Okay, And so I have to sort of help you visualize the numbers a little bit to make sense of numbers. I arranged the numbers in decreasing order. So the deviations, the difference is arranged from the most positive to the most negative here. So what I observe is that the numbers here, the difference is about in the order of like 2 percentage points. So in objectively speaking, these numbers are small. Okay. So what I think ELD said was that we expect numbers up to 4 percentage points. So this is sort of the correct ballpark figure that we saw. Also, like the numbers, if you look at it, the positive and the negative, they're about equally spread on both sides. So this is what we expect. Okay, unbiased errors. This is sort of like the numbers, the figures that you expect. Next slide. Okay, so this will happen this year, just for the SMCs only. Okay, so we do the same thing again. Repeat the same graph. Same tables. First thing that pops up is that the top row here, Kebun Baru, overestimated by 5 percentage points. It's a bit bigger than what we expect. The other thing that we noticed was that there's a lot more positive values. So in some sense, the sample count appears to be like overestimating the actual vote share for PAP more than one might expect. So the question is like, is there something here? So what we're going to do in the next few slides is going to ask the question like, how unusual were these numbers? How unusual were these numbers given the actual vote share? Next slide. Okay, so here's the results for the GRCs here. So GRCs is different from the SMCs in that the GRCs are much bigger. There are multiple constituencies. So in these cases, you draw a much bigger sample count. And so they are much better estimates of the underlying, the actual vote share, vote fraction here. So this reflects the numbers here. The percentage points are much smaller margin, they're much better estimates. Also, we always saw is that in both the 2015 and 2020, the deviations were sort of equally balanced on positive and negative. So perhaps not too much to say here. Next slide. Okay, let's zoom on this one basic question. Let's answer a simple question, a simpler case. Okay, let's look at what happened in Hougang. What happened in that day was that the Workers' Party had 61.19% of the vote for the valid share and PAP 38.81%. The sample count that evening was 58 to Workers' Party and 42 for PAP. So the question I'm going to ask is how likely, or you can say how unlikely were these numbers that we observed. Okay, next slide. Okay, so let me try to formalize what this question of how unlikely is in the following sense. So what we do is let's assume we take all the voting states from Hougang, okay, from all the upon districts, we mix them in a single box, put them in a single urn, and then mix them evenly. The next thing we do is to draw 900 voting slips. Okay, 100 because there were 9 voting stations. In each station you picked up, you drop 100 voting slips. So that's what actually happened on that evening. So the question we're asking is given this scenario, how likely is it that we draw 42 or more percent slips for the PAP? Next slide. So we can do this in the following sense. Let X be a Bernoulli random variable. So a Bernoulli random variable is it's a random variable that is either 1 or 0. It's in this case going to be set to 1 with probability P equals to 0.3881. That's the probability of that's the fraction of the PAP vote share. Let's draw 900 random variables from this distribution independently. So the question is, what's the probability that the sum of these random variables is going to exceed 9 times 42? So that's in other words, a fraction of more than 42% for PAP. So this number, this quantity, turns out to you can compute it in terms of the regularized beta function. It's a specialized function that's used quite a lot in statistics. In this case, you compute it, you put the machine, you compute it, you get a number of approximately 0.023. So to put it this way, what it means is that if you actually put out, to just rehash what I just said, if you actually put all the voting slips together in one box and you put it up randomly, then there's a chance of about 2.3% that you get 42 or higher in the sample count for PAP. So that's the number. Okay, next slide. So there are some caveats. Those are caveats that Shen Ting mentioned, so I will not spend more time on this. Next slide. Okay, so what we did here so far was to compute this 2.3% for one SMC for Hougang. This we have to stress is that this is done in isolation. So this is done on its own. It's sort of like not so it doesn't regard the rest of it. Now, if you keep doing this, you keep repeating this process, what you see is that if you do this often enough, you will eventually encounter one that's extreme enough. One that will say oh, this is going to happen with a very small percentage. This will happen by chance. It doesn't mean that there was something strange. It just means that this was always going to happen because you do this often enough. Some of these rare events will eventually happen. So how do we treat these sort of multiple scenarios? How do we deal with this? This is Shen Ting will take over and tell us how we're going to do this.
Okay, so this is what we call the multiple testing problem. And we said that for multiple hypothesis tests, we denote them H1 to Hm. And we reject the null hypothesis if the test is significant, i.e. if the p-value is usually, when you say 0.05. Okay, the proportion of the false discoveries that you're going to get is going to just be the test is declared significant when it actually shouldn't be, over just all of the number of tests that are declared significant. And the expected value of this is just called the false discovery rate. Okay, so given that there are in total 35 GRCs and SMCs combined together, if we do hypothesis testing for all of them, you just expect to see one significant result just purely by chance. So how do you control for this? Okay, so what we do, this is an idea that was first introduced by Benjamini and Hochberg in 1995. What you do is you sort the p-values in increasing order, and then for each of the p-values, when you sort them, you compare them to the index divided by the total number of tests you do times alpha, where alpha is the desired rate. In usually case, we use 5%, so alpha equals to 0.05. And you find the largest value of k where the p-value, the sorted p-value in the kth position, is less than or equals to the proportion times alpha. Okay, and this is known as the Stepup Procedure. And what you do is you reject the null hypothesis for all hypothesis tests from 1 to k. Okay. So this is kind of an idea of what you do when you have many p-values. You sort them from smallest to largest, and then you draw a line that is to alpha, and then when you have the sorted index, you basically just see which is the largest k value where the p-value is still underneath this line. Okay. The diagram is actually from my own master's thesis back in 2012. So what did we get from this? So we already applied this to the p-values that Yong Sheng calculated in Python using just by calling the binomial function. And there were no significant results actually using the two-sided test. So we're going to test for both sides whether there's any unexpected results. There's none. But if we just use the one-sided test, which is the idea that the sample count, the alternative hypothesis that the sample count is actually overestimating the actual vote share, then only Kebun Baru is significant. So this is quite different when you actually go and look at the full results, which is if you don't do the multiple testing, you will actually find that there are quite a number of constituencies which are significant if you just apply the 5% significance level. But when you control this by applying for multiple testing, only component borrow is significant. And that's if you just use a one-sided test. So guess what's the conclusion, right? Is there imperfect mixing? We don't know. I mean, the fact is that when you're dealing with, when trying to physically mix things like ballot slips, even to the best of efforts, it's very hard to maybe get a perfect mixing. Okay, so but I think in general, what we've shown is that even with the so-called skew that we kind of see or bias that in this year's sample count versus actual count, the sample count is actually reliable. And most of the time, it's actually indicative of the actual result unless it's really close, right? So if you follow what the ELD said, for SMCs, it's usually about plus minus 4%. And for GRCs, it is about 1 to 2. Okay. So that's it. I guess there's a bonus insight from this year's results. And this is actually thanks to another friend of ours, Kenneth, who first spotted this. I mean, multiple people spotted it later, but he actually spotted that if you look at this year's results, just by tabulating by the constituencies in which Workers' Party contested in, they actually got a higher overall vote share versus the PAP. Okay, and we've reached the end of the talk. First of all, I personally need to, of course, thank my co-speaker Yong Sheng, because when he saw this, he thought about it and he also did some analysis and we talked about it together. That's why we end up with a more complete analysis. I also like to thank Beyond Su for actually counting the polling, helping me to count the polling districts from the ELD documents on the actual night itself. A few other people, I've mentioned Kenneth, two other of our mutual friends, Jingyi, who was discussing with us about the multiple testing. Sean also gave some helpful comments. And I have to thank Ku, because actually Ku was the one who came and said, hey, I think this is worth a talk. And I guess the point is that, this is not actually a very complex analysis. Most of it I did in Google Sheets, just with Yong Sheng's side analysis for the function he needed to use Python, but that was it. We fed it back into Google Sheets and we did the multiple testing correction within Google Sheets itself just by sorting. Yeah.
Okay. Thanks, Shen Ting. Yeah, you got references that you want to share the references or?
Yeah, so I did a write-up, I reposted it on Facebook. That's where I think Ku came and find me. And the actual sheet is on Google Sheets. I can probably just open it for a bit, given I have a few more minutes to show. One of the idea I actually got is actually Nyam Shitong. He wrote an article from GE 2015 and he wrote about the same thing. How accurate is the GE sample vote count? And for those who are still maybe a bit confused, you can read his article. I think it's quite a good read as well. So I don't think this is not an original idea, and it's just that I happened to decide to do it this year because of the late results. Okay, so hang on. Yeah, so the numbers were taken from the Gazette, and then you can kind of see. So on the actual night itself, even if you look at Sengkang, it's a bit small. Let me just zoom in. Okay, for some reason it's not zooming in. But...
Okay, I think what we can do is we can share the link on our the Facebook group page, right?
Sure, thanks.
Yeah, we can share it over there, and then for those of you who are interested to know the formulas behind and all this, you can have a look at it. As to why I think this is worth a talk is because I think a lot of people's on their mind will be, hey, is sample count really representative, or what kind of range are we looking at? And I'm glad you all actually presented the range. I think it's 5248 for GRC, and then I think it's 4654 for SMC. Am I correct? If I remember the numbers correctly, yeah. Okay, sounds good. We have too much. How to put it? We have too much technical programming contents and all this. So I think it's good to sometimes have some statistical contents as well. We cannot always be doing machine learning, right? Sometimes p-value and hypothesis testings are also quite interesting, depending on the application. Okay. Any questions from the audiences before we move to the next speaker? Sean, yes, it's recorded for replay. Okay. Okay, I think they are still trying to figure out the statistics. I also took down the Benjamin Hopbert. What's that one?
Benjamin Hopbert. Yeah.
Yeah. I'll took that one down. I probably will have a look at it. Wikipedia will be where I go next after this meetup. Okay. No questions, or maybe if you got questions, if you thought of questions, you can post it in. So let me thank Shen Ting and Yong Sheng. Thanks for sharing. So I'll now bring you all to the backstage, and I'll now invite the next speaker to join us. So hold on, let me. Hello. Hi. So our next speaker we have Siddarth. Siddarth, I think there's some feedback from your mic. You want to maybe see whether you can reduce it?
Is it okay now?
Yeah. Now better. Although there's still some feedback though.
Is it fine now?
Yeah. Can. But I think your sound may be a bit soft though. But let's see how it goes. If the sound is too soft, then please let us know from the comments. So Siddarth, you're going to share on reinforcement learning, right, in finance?
Yes, I do.
Yes. Okay. So without much further ado, I will pass the stage over to you. Okay.
Thank you. So hi everyone. Thanks for having me here. So my name is Siddarth. I used to work for Prudential for past 4 years in the AICUE, and now I'm currently on a hiatus, trying to figure out the algorithmic trading on quant industry. So I was excited by the concept of reinforcement learning, and I found that it's not vastly applied in the finance industry, not just in quant, but even in insurance and other verticals. So I thought, like, okay, why not let's try out RL in finance rather than the plain machine learning. So here I am. So in this particular talk, I'm going to introduce the concepts of the fundamentals of RL. What are the core verticals that operate the RL model, and how can it be applied to the financial world? So let me start. Okay, so this is the outline of this particular talk. So I'm going to introduce the what is RL, the components, the algorithms that are used, and the model-free RL and model-based RL. How trading can be used. So I'm going to focus more on trading as of now, and then I'll talk about the challenges and the future scope. Going ahead. So this is the overview of RL. So RL forms in the niche intersection of a number of verticals, such as your reinforcement, the machine learning, reward system, optimal control, and operational research as such. So for us, it's mostly the machine learning part that excites the most, combined with the reward system. This particular image is obtained from David Silver. So David Silver has a very good and rich course on reinforcement learning that you guys might be interested into. This let's go into the characteristics of RL. So what is RL? RL is a branch of machine learning which relates with what reward or what reinforcement am I going to get by performing an action. So for each action that it takes, it expects a reinforcement. It might be positive, it might be negative, and it tries to obtain the maximum reward in the positive direction and tries to take the action for each state. And this is quite different from the traditional supervised and unsupervised learning, where you have a label and you regress your model against those labels or the values. But the reinforcement learning tries to pick up the actions that would actually maximize my reward. And a reward, when I speak about it can be very different with each phase. So let's say I'm in a casino and I have 4 to 5 arms to pull out to get the lottery. That is itself, it's a variant of RL, which is called a multi-arm bandit. And when it comes to the real world trading, then the money that I get, it's a reward. So this particular concept can be applied to a wide arena of field, but the reward and the policy is the crucial part of how you design it. So these are the core components of RL. So policy. So policy is the agent's behavior function. How does the agent or is going to behave for a transition from particular state S0, say, to state S1. So there are basically two types of policies. One is the deterministic policy and second is stochastic policy. When I say deterministic policy, it is mostly to deal with there is a fixed path by which the agent has to go from each of the states in order to achieve his goal. Let's say from S1 to S2 to S3 and S4. Let's say S5 is my final goal. That would be a deterministic policy. And what is stochastic policy is that there would be a probability assigned to each state. So there is a probability that the agent would go from S2 to either S3 or S4. So there is a probability assigned to each of the states, and that is a stochastic policy. The other component is the value function. Value function is just the cumulative sum of all the rewards that the agent is going to get for each action that he's going to perform. The next one is the model. So basically model predicts what would the environment do next. So it's basically on the observability of the agent across the environment. It tries to see that at what state am I going to move into, and what is the reward that I'm going to get by moving into that particular state, and it takes action based on the reward. And speaking of which, reward is anything that the model receives as a reinforcement for each action. So because we are in the financial world, I would say every dollar that you earn in your bank, that's a reward for the model. Moving on. So reinforcement learning traditionally has this simple concept of observation, your environment, action, and reward. So think of it as a brain in which constantly observe its surrounding. It takes some action. It learns on its own that okay, some actions I should not be taking right now, or some actions I should be taking it in the later time, and that's how it maps its reward. So there are a lot of variations in RL. I'm not going to cover everything because it's a huge area, but I'm going to focus on model free and actor critic model, which is an intersection of both. So these models, when I say model free, model based, and actor critic, are nothing but everything is focused on 3 to 4 concepts of the Markov decision process. So before I jump into that, I just wanted to introduce the huge hierarchy of algorithms that is available in the reinforcement learning. So OpenAI has drafted this beautiful chart where you could see the big hierarchy of algorithms that is available. So model free, model based are the two big components. And speaking of which, of model free, there are policy optimization and Q learning, which I'm going to focus more. The second one is the model based RL, which is the most famous AlphaZero algorithm is actually based on the model based RL. If you're interested more on each of the architecture, feel free to go to the link mentioned, and you can learn. The next important piece differentiating the two things is model free and model based. So when I say model free, the model is trying to get some reward based on some trial and error. Let's say let's go to that casino example. I try multiple combination randomly at the start. I learn by mistakes and I note it down and go on and explore and exploit my iteration. However, model based is more on creating a mental map to work out on the longer value of each action at its current states. So it basically computes its value. What will happen if I go to each state, and it is kind of an unbiased, so it will give equal weightage to each state. It will try out each state and then make a mapping and then take a decision. Whereas model free is just it will start randomly, it will quickly converge to a path that it feels the best and take its decision thereon. So these are two different ideas. So one simple example is as given in the diagram below. So if you are going through a model free approach, you stop at a junction and decide that okay, today is a Friday evening, I should just go straight and avoid the freeway. So this is by the past experience replay that you have encountered by n number of iterations, and you just take this decision. Whereas in model based, you actually calculate for each street and each road to your destination and say, okay, by this approach, I get the longer reward, so probably I should avoid the freeway and go straight. It's basically just the difference between the calculation of the values. So these are the two different models that I think everyone would be familiar with the AlphaZero game, so it was quite famous. So DQN is the deep Q network, for which this is a model free approach, and the other one is AlphaZero, which is a model based approach. Although technically some of the components is indeed model free, but it does have a mental map of creating the structure. So when it comes to a game, so let's say for the sake you have a game with 2 players. At each step, a model based model will try to see that what are the n number of combinations that I can take at this particular step, what will be the step that my opponent is taking, how will it impact me, and there on and therefore. So if you could see, there's n number of possibilities that goes on, and sometimes and also the function is such as that it's exponential. So if you have too many of actions, then the computation can go quite high, and even the q value, which is basically the one that goes behind the value, the model, so it becomes complex. And I'll jump into the mathematics in a moment. So this is Bellman equation. Bellman equation is one of the important equation on which the q value works. So if you could see, this is fairly a simple equation. It states that it's a summation of the reward that the agent is receiving for the given state by an action, plus the maximum value it has obtained previously in its older steps. And you can see the gamma function here, which is the discount factor. So it controls the importance of long-term rewards versus the immediate one. So it is as simple as an LSTM for get gate, which determines how much it has to remember and how much it needs to forget. It's something similar to that. So the important characteristic is that we depend on the Markov state assumptions, and the recursive nature of the Bellman equation allows the rewards from feature to propagate to the far off past states. So I'll jump into the Markov state assumptions in the next slide. So Markov decision process MDP is the the main function on which most of the RL models are defined. So almost all RL problems can be formalized as MDPs, and there's um, a diagram at the bottom where you can see that for a student from class 1 to class 3 and then passing, all are defined as states. So what it basically says is that for predicting my next state, all the data that I need is just the present, and it doesn't need the past historical data. So that's what the fundamental property. So as you could see that if I have to move to class 2, the probability is 0.5. But at the same stage, if I spend too much of my time on Facebook, then and I get stuck in that particular loop with high probability, possibly I'm just going to stay there and never going to move to the class 2. And if I going to sleep a lot, I'm going to get stuck there. So that's how the state transition matrix is calculated. So this is a phi tuple on which the Markov decision process is designed. The states, all the states in which the agent is going to go to, all the actions that the agent is going to take, the reward, and the probability, the transition probability function, which I just mentioned in the previous chart. And P naught is the start state distribution. So it's just the initial state. Moving on, the Q learning. So Q learning is it falls in the model-free approach. So what it does is generally creates a table of for each action and for each state what I'm going to earn. So let's say in this particular game, you see that if the robot is going to go to right, it is going to get some points, but if it comes to down, it's going to blow up. So let's say the end is going to get a reward of +100, and for each the electric star, it's going to take 10 points, and if it hits the bomb, it's going to have 0 reward or -10 reward. So the model will take each step in each directions and try to create a table and store all the values. So by doing this, it tries to know, okay, if I approach one particular path, I'll receive the highest reward. So maybe it is going to go directly to the right and to the bottom and go to the end and say that, okay, here's my reward. But alternatively, it can also go and collect all the stars in its path and then go to end, then it has more reward. So this is the way it will reach the end and store the Q values. So when it comes to deep Q learning, we obviously have to have theta, which is the parameters that the model is going to learn throughout the model run. So how the cost would be calculated is simple. We just rewrite the old equation of Q value, and we have to sorry, we have to update this particular Bellman equation as a simple update rule. So there is some difficulties in Q learning is because of large set of actions. So let's say you are encountering a problem where the number of states is close to infinite, and you cannot keep calculating the values for all the states and all the actions that the agent can take, and it could be cumbersome even to maintain that table. This is where the policy learning comes into play. The policy gradient is much more robust than the Q learning, so it simply evaluates which action should it prefer and doesn't try to evaluate each action. So it is more of trying to get the probability of selecting an action as output. So instead of mapping from theta to Q value and then the policy, it directly sticks from the parameters to the policy. It doesn't calculate the Q value. And how do you optimize the weights? So the optimization in the previous one was using Q values. Because Q value is not calculated here, there is a separate approach here, and we can start with a simple plain vanilla genetic update rule, and I'll come on to what's J here, but the theta t plus 1, so we are for the next state we are getting the current state's parameters plus the learning rate and the J. So what's J is the performance measure, which is the most crucial one. So in this particular case, J is nothing but the cumulative sum of for all states what is the key value plus the probability of the action. So uh, the summation of all the q values for a certain state with the probabilities is called state value function. So as you could see in the next equation, which is the um, we calculate the gradient, the change in the j theta of t. This is given by this particular equation, gt, and gt is the total accumulated reward from step till t till end of the episode. So what I say by episode, it's much mapped to the epochs in a deep learning. So for each time t, you just calculate what is the total accumulated reward. The derivation of this particular equation is given in the reinforcement learning introduction by Sutton and Bartow. It's a very good book, which actually goes from the fundamentals and into niche mathematical derivation. So this is an example where even policy Q learning doesn't help a lot. So as you could see, this is a this is a slide that is obtained from OpenAI. So this is a cheetah that is trying to run, and if you could see, it is running in an inverted position. So here the policy design was that if the cheetah is going forward, it is going to get a reward, but it was not stated that if it is going to get a reward if it is going straight on its non-inverted position. Hence it keeps running in that particular direction and goes out of space. So designing the policy is more crucial. Hence comes a picture of actor and critic. So what an actor and critic is that so an ideal scenario would be that the agent would learn the policy in a similar way of the gradient policy method, and also understands that the importance of state and action knowledge, which is in the Q learning method. So actor critic basically combines the both, and we get best of both the worlds. So in this particular technique, what we basically do is that for each action we get the Q value for each state, we map it back to the policy gradient, and we get the final output. So in this particular way, if you see, I have updated the equation here. So in space, in the place of the j, I have replaced it with the q of st and at, which is the q value in general, which is from the critic. So we combine both these algorithms together, and we find the model working better. Okay, so this is on the fundamentals of RL. Now I'm going to go deep into the applications of RL interference. So being in the finance industry for more than 5 years, I have seen that most of us do machine learning such as classifications, forecasting, and regression problems. But I feel that RL could be applied into some of the spaces, and such as portfolio balancing, insurance policy pricing, robo advisors for asset allocation, etc. On a personal note, I specifically like to use RL for stock market trading. So I being a passive trader, so I use this particular technique now and then to find out its advantages. So basically you could use the data from either stocks, your assets, your bonds, forex, etc., and try to architect the problem statement into the RL language, such as you have to decide what is the actor going to look into, what is the critic going to look into. So if for an example, I can say that if I want to have an asset that is going to give me a return which is consistently higher than 10% per se, but I need not take any risk that can end up in negative yield. So this particular problem, you can have the critic saying that, okay, I don't really care about the return going above 10%, but I do have the problem that I should not go in the negative area. So it will try to play less risky and will hedge its position accordingly. So this is an example that I wanted to point out. This is a recent one of Tesla, where it had gone down literally because of it didn't make it to the S&P 500 because the P earnings was not up to was too high. That means the stock was overvalued compared to its peers. So basically, the rising that the bull that the stock has seen is basically based on the investor confidence, and basically the drop at this particular point cannot be really expected because it's morely news driven. So uh, for a for a single model such as LSTM, where you can have 3 to 4 classes. Let's say I can predict if it's going to open high, maybe buy, hold, or sell. But let's say I have a number of stocks and I need to maintain a portfolio. I cannot sell too much, I cannot buy too much. I also need to have certain amount of cash in my liquidity. So how do I do that? So for these particular instances, if we have an RL model where you can pass on the data for various information, then the model could try to learn based on the criticism, or I mean the Q value. Let's say if the risk for the particular stock is going high on the Q value, then you have to probably understand, okay, I don't have to be too risky because I have to limit to my benchmark return. So this is a difference between the Microsoft and the Tesla's PE. So even though by momentum of the stock and the way the stock was rising previously, all the technical indicators such as RSI, the Bollinger Bands was projecting upwards, but a single sentiment pulled down the entire stock value. So we have to give the RL the entire environment. So what I mean by entire environment is that the model needs to know what is available in its observation. So it needs to know the trading position, cash value, not just the stock trends data, but also the time at which it's going to enter, the macroeconomic data, Twitter, etc. So for another example is just like Musk said that he himself feels that stock was overvalued and it dropped by 10%. So these things the RL model needs to know. So let's say you have a suite of 4 to 5 models. One of the model controls the signals that the tutor is getting in, and the second model controls the technical indicators, and the third model controls the risk. And the RL model as an ensemble would try to control these 3 algorithms. It will try to say that, okay, because I'm looking for more of profit this time, even though my risk is saying that I don't need to invest more, it will still invest more and try to get better returns. So this is one of the application. And when it comes to the objective function of RL, I have used Sharpe ratio. Sharpe ratio is nothing but how much return are you making adjusted to the risk-free return. So anything above 1 is a safe. So if you are, even though you are making good return, but if the entire portfolio becomes too risky, you might want to stay away from it. So one such example is, let's say the model made a profit of 21% today, and it then dipped to 10%, then it went to 31%, and then got back to 2% or -%. But if you even though you sum the entire return, you might be in the positive node, but there's a lot of volatility here, and probably you don't want to be in that particular position for a longer run. If you are looking for a short-term target, then you cannot of course play. But if you want to have a long run where the objective is to have a consistent return on an annualized base, then probably you'll be sticking into something called Sharpe ratio, and this would be the policy with respect to the reinforcement learning. So this is my personal trading numbers. So I have a Sharpe ratio of 1.2. But if I compare with my previous models that I have built for the Indian stock market, the returns are very much similar to what LSTM made. But what I also seen that the training time is longer, and at the initial time of the learning time, the model will try to get as much returns as possible at the start, and will will very strongly accumulate the funds and try to get the peak of uh, at a higher time. So let me go to the slide here. So if you could see, there are a lot of peaks out here. So let's say at the initial time you say that 10% profit, it's all I want to make. So the moment the model the model sees that from your initial position you have gone at a peak, as a smaller peak, it will sell off your position. But maybe there is another bull that is waiting for you, and you might have received 15% or 20% return if you had waited for uh, T more trading session. So this comes to exploitation and exploitation trade-off. You also want to control how much are you willing to wait with respect to the trade session, or you want to make immediate profit as soon as possible. Going further, these are, I have few recommendations if you want to try this out. So there's a library called Zipline, which is very good if you want to backtest any of your models, and this is mostly paper-based backtesting. So it is quite useful to learn. You can start as simple as mean aversion algorithm and or simple forecasting, and slowly you can compare the performance of the algorithm as in you improve your models. And this is an excellent repo, the Awesome Quant, which has which is a repository of all the library related to quant for each and every language from R and Python and so on. So I would like you guys to check this out. And the final is the challenges. So what I saw is that RL is quite sensitive. It overfits much faster rate as compared to LSTM, and also because I'm not able to give the whole view, such as the politics, what is happening, maybe any Trump's comments that might impact my model position, or is there any war that is going on, these kind of things. RL doesn't really give much weightage, and that is one particular challenge that I saw. Although I'm still learning and trying out new papers, I have also included the papers that I have tried in the references, and want you guys to check it out. And that's it. Let me know if you have any questions.
All right. So yes, if you have any questions, feel free to post it online. Questions, anyone for Sid? Okay, I'm going to bring Yong. I think Shen Ting will be the one taking up the question, right? So let me bring Shen Ting to the front. Okay, Shen Ting, I think we have a question for you. I think let me show the question now. Okay, so Ice Water is asking, sounds a bit strange, but yeah, Ice Water is asking, is it possible to ensure better mixing of the sample ballots? Let's take one question at a time. So let's answer the first question. Is it possible to ensure better mixing of the sample ballots?
Well, so first of all, we don't know how the mixing was, the sampling was done. Of course, better mixing is of course important. This year, we have it's a very different election because there was a reserve time slot for the senior citizens to vote. Maybe this might have introduced some, unintended bias in the sampling. We don't know. without actually, knowing how they do the mixing, I can't really say much. And I think there's also some physical limits.
Okay. So the second question is, can we suggest improvement to the process? But I guess like what you mentioned just now, if we don't really have a good idea or understanding of the details, probably that one may be a bit of a challenge, right?
Yeah, because I mean, if anybody has suggestions, you should take it up with ELD. Yeah, I can't answer on the ELD's behalf.
Okay, can. So yeah, if you got questions for Shen Ting Yong Sheng and Sid, right, please continue to post it. Sid, we do have a question for you. Let me show it now. So do you link up your RL model to live trading, and what is your setup if you have done so?
Sure. So I do not have linked my RL model to live trading. So basically, as you know, we just have 5 tickers: the open, close, high, low, and the volume that is traded, and that gets usually updated at the end of the day. So I have set it up in such a way that I just get SMS triggers once my model senses, and it runs at the end of the day. So I have not directly linked it to the stock market. I just analyze. I get the recommendation from the model, think about it, and then make it read. I'm still working of linking the model to directly the trading platform. So because I'm from India, I have used there are APIs which cost you, such as Zerodha, which is one of the trading platforms where you can obtain an API and you can pass on your signals, let's say buy or hold or sell to them by consuming their API. And there are a lot of also articles that's available there for getting a good trading setup. But as of now, I'm still backtesting my algorithm heavily before I go live.
Okay. Great. Any more questions? Ryan, your question, is there a link to the slides? I think Shen Ting has already posted it on Facebook. You can check it out. As for Siddarth, we'll see whether we can get the slides from Siddarth, and we'll share it. But for the audiences, right? Yeah, the videos will be posted on YouTube, but you'll be at the Google Developer Space YouTube channel. You can check out their channel as well. They have a lot of other videos. I just back in, right? See, just are very nice, right? You all sponsor us, and then I will ask people to go to your channel.
Ambassador. Yes.
Yeah. I need more swags. Yeah. Okay, so yes. Questions, anyone? Okay. Okay, I think no more question already. So I think let me bring. Okay, so thank you very much to our speakers, Shen Ting, Siddarth, and Yong Sheng. So thank you very much, and also thank you Google Developer Space for sponsoring the venue, and of course, more importantly, is our audience. Thanks for spending your time with us here today for September meetup. So this is all for the September meetup already. So with that being said, Justin, anything else you need to share with the community?
No, none for me. Yeah.
Okay, can. So with that being said, thank you everyone. We'll be ending the stream now. Thanks. You can check out the video again later on. Okay, thank you. Bye-bye.
Bye.